Hello and welcome to a presentation by NDT Technologies titled, Why Do We Need Continuous Wire Rope Monitoring? So first, some definitions. Wire rope NDE is referred to as non-destructive evaluation examination. This is a quantitative measurement for things like defect type, location, size, etc. It includes MRT and visual inspections. MRT stands for Magnetic Wire Rope Testing. Let's talk a little bit about wire ropes. There's a bunch of opinions related to wire ropes, including that wire ropes are low-tech commodities without much interest. Wire rope failures must be accepted as inevitable. We believe this is false. Now let's look at some facts. Wire ropes are complex machines with a great many moving parts. Wire ropes require attention, skilled operators, careful maintenance, inspection, and lubrication. Wire ropes are safety critical and represent single points of failure. Let's look into some of the aspects where wire ropes are safety critical and single points of failure. Certainly in this respect, the wire rope holding up the load here represents a safety critical operation. Failure may result in death or serious injury, loss or severe damage to equipment or property, and potentially environmental harm. Wire ropes are also single points of failure, meaning parts of a system whose failure will stop the entire operation, and ropes are single points of failures that usually cannot be eliminated. Let's look at some wire rope deterioration modes. Magnetic wire rope testing, or MRT. Why would we do this? Let's look at some facts. Modern wire ropes deteriorate internally without visible indications. Visual inspections are ineffective. Internal deterioration in multi-strand in IWRC ropes. Typical deterioration locations within the multi-strand rope, as shown here, can be shown in this inner core. So again, the red highlights the deterioration location. For an IWRC rope, here in red you can see the deterioration location. Notice both of these represent an internal location which may not be visible from an external inspection. Let's look at some rope retirement philosophies. From a statutory or life policy, retirement could be at certain prescribed intervals whereby the rope condition may be truly unknown, versus a retirement for cause where the retirement is based on non-destructive rope examinations and evaluations, again referred to as NDE. Under this condition, the rope condition is known and can be tracked and trended over time. Let's look a little bit more at retirement for cause. Retirement for cause is based on MRT inspections and visual inspections, as well as auxiliary information. It is our opinion that MRT inspections plus the auxiliary information represent the key retirement for cause criteria. Visual inspections, although still important, may not represent the true condition of the rope, as was evidenced by the internal deterioration of the multi-strand and IWRC rope cases previously shown. Let's look at the MRT inspection for a continuous rope monitoring system. There are intersections with visual inspections which could capture the same criteria, and there's auxiliary information such as rope construction, operating conditions, damage mechanisms, and rope history. As discussed previously, we believe visual inspections are important, but may not represent the true condition of the rope. The intersection of these three represents a complete wire rope examination, which can be the basis of retirement for cause. Subsea crane inspection logistics. First, we'll look at some of the early attempts. Here's our problem statement, which is rope deployment has to occur for the inspection. Here is a picture showing some of the rope being deployed with the tugboat here. Here you can see the inspection equipment, as well as the tugboat in a farther view of the picture. And yet another view. The present practice is to take the vessel to a deep water location, deploy and perform an MRT inspection of the rope, retrieve and do an MRT inspection of the rope. This represents a high cost of deployment. Here is a typical offshore inspection. As you take your vessel to the deep water location, you're accruing the cost of deployment. 6 figures is a typical estimate. You can now deploy and do an MRT inspection of the rope. Notice that this is time and money that's being accumulated as well. Now you can retrieve the rope and perform your MRT inspection as well, further accumulating additional cost due to time. And now you can return to port, further accumulating additional cost. In summary, you're burning a lot of money to perform your inspection. A continuous wire rope monitoring system, or CRMS, will be explored. Our continuous wire rope monitoring system can be used for an inspection during actual winch or crane operation. It helps eliminate considerable cost for deep sea vessel deployment and will allow implementation of retirement for cause policies by constant supervision of the rope condition. Here is a typical subsea crane CRMS inspection. Notice the various parts, including a storage winch, an optional traction winch with heave compensation, the sensor head, shown here in yellow, with associated signal electronics, attached rotary encoder with feedback information, and a connection to the laptop to display the information and to be used in report writing. Once the load is attached, we'll perform our MRT inspection during the deployment. Here is an actual view of the CRMS system in operation for an A&R winch. For continuous rope monitoring, the large air gap avoids damage to the rope and/or sensor head. The air gap is also required because the rope is usually covered with lubricant. Continuous rope monitoring is useful for rope life prediction. It allows for optimum rope operation, can extend rope life while maintaining safe operating conditions, schedule rope replacement well in advance, helps eliminate downtime for unexpected activities such as rope replacement, and can help establish maintenance schedules, as well as alarms, warnings, and notifications. It is also a preventative maintenance tool which helps with the early detection of corrosion, which allows immediate corrective action through improved rope lubrication. Accelerating wear and interstand nicking can indicate a need to reline sheaves to stop further degradation. Monitoring the development of local damage at the crossover points of the rope on a winch drum. This way, the operator can determine the optimum time for repositioning the rope on the drum. Upon completion of the MRT inspection, the use of software such as our NDT Care Vista software can be used to display the data and to perform a complete analysis, which can then later be used for report writing and trending analysis. Our computer-aided rope evaluation, in short, CARE, software is used for analysis. For this particular application, we'll investigate an A&R winch rope with a 78mm diameter that was part of a spooling operation in Spain. Okay, we have opened our NDT CARE Vista software. So first we're going to click Open File. Select the file type, in this case it's a text file. We're going to select our A&R rope example. You can see here that it's just under 2 GB file size. And then I'll select Open. And once the file is open, you'll see a log entry here. I will then go to Display LMA LF Charts. A pop-up appears asking for the number of meters per tab, specifically to select an integer number of meters of data to display per page. The file opened is 3210 meters long, so about 3.2 kilometers, and then an overview plot will appear on the first page. So here I'm going to select 250 meters per tab. That'll give us a coarse level of zooming. A pop-up will appear asking how you would like to display the data. I will select a forward direction. When the charts are finished, notice a log entry appears here, and you can actually see the plot back here. A quick inspection of the chart is you will see LMA in percent followed by LF, and on the bottom trace you'll see on the left axis rope payout in meters, and on the right axis rope speed in meters per second. The x-axis here is rope distance inspected in units of meters and is the same for all plots. Notice the 250 meter tab increments are shown at the top, so we could essentially scroll and look at any one in particular. For example, we see this spike here in the 250 to 500 range, so I will click this, and then you can see the spike in a little bit more detail. You can then go back to the overview plot or any other tab of interest. I can change my axis setting by going into Properties, Change Axis. A pop-up appears, and now you can enter the scaling that you want. So for the LMA, I'll say -1 to 1. Similarly for the LF signal. For rope payout, I will just go between start at 0, go to the 3230, and then rope speed, since it's positive, I will go 0 and a max of maybe 0.5 and hit OK. And when completed, you can see the zooming as we have selected. If we go back to any tab, we can see that the axis scaling has been applied to every tab. We can now look at this in a little bit more detail. Notice that the LMA is far less than 0.5% here on average. This is a new rope, and so this would be expected. You can consider this rope noise as opposed to signal noise. The rope noise basically meaning of the little gaps, etc., within the construction of the rope. So this is basically will establish a nice baseline for your rope. The large spikes are essentially lined up with the spikes in the speed and most likely are due to some stick-slip operation. We can now start to look at things like our WRR feature. A pop-up appears asking for a reference scan length in units of millimeters. The reference scan length is typically chosen to be equal to the rope lay length. The lay length is approximately 6.25 to 6.5 times the rope diameter. So given the rope diameter, I will enter a nice round number of 500 millimeters for the lay length and hit OK. The plot that appears now shows the LMA in percent followed by our WRR signal, which stands for wire rope roughness. Notice in the middle of the plot you'll see a slider here referring to the scan length that we have previously entered as 500. The purpose of the slider is for ISO 4309. Defines lay lengths between 1 and 5 times. So here is our 1, and notice that we go up to 5 times the 500 or 2500. So it allows us an opportunity to inspect this. So at the current setting, we see on our LMA a green signal, which is our max BLMA signal. and the blue is the actual BLMA. And then down below on the wire rope roughness, because of the spikes, not much seen, but there are two things. So for now, I will do the lower end of 4309, which is the one lay length default that we had set in of 500, and I will click Save WRR Settings. Once that has been finalized, you'll see the log entry here with the scan length selected as part of the log, and you'll also see it here with the scan length on the chart. We can now click on the actual chart, go back to Properties, and change Axis again. We'll leave our LMA settings as is. Notice that it saved it from before. We will go to 1%. Once that zooming has occurred, we can click the plot. As mentioned before, the LMA signal has two different signals riding on it. First is the green one, which is our max BLMA, and then the blue, again, which is the actual LMA signal. Notice now, after the scaling change, you'll see the two different signals. The black one is our wire rope roughness, and the green is what we refer to as our skyline plot, which is essentially the difference between the two LMA signals shown here. We can then zoom in as shown previously. And even in here, you'll see what looks to be like a lot of clutter or noise. So since we've kind of limited ourselves relative to this 250 meter zoom, we want to introduce some additional features. Notice the plus and minus right here. If I click the plus, that allows, and hover over it, it says to zoom in. So I will click that. Notice a small crosshair appear, so maybe I want to start at around 800 meters and just go a little bit right here. We can choose to zoom in that range. Notice that you can see here a zoom of this signal. If I were to double click on this, it'll now go back to its normal. Additionally, I can zoom the bottom one as shown here and see a great amount of detail. There's also a pan button here, which allows me to move the signal back and forth and up and down. I can always reset it by double clicking and it will reset. Another feature we can do is, let's say there is some part of the rope of interest here, maybe around this 2000 meter mark. So maybe I click this tab, zoom in, and there's potentially a feature here that I would like to look at. Again, I could then go in and zoom in a little bit more. And perhaps there's a feature here, and if I want, I can then select this button right here, click it, and select a point on one of the graphs, and once I click that point, notice a marker appears. It actually tells me the actual X location here, in this case 1957, which is again the location on the rope in meters, and also the Y-axis, which in this case is the percent WRR. So notice that we're roughly here at 0.35%. If I hover over this, notice that it allows me to move this. So I can move this. So in this case, notice what I'm doing is I'm riding on the green signal here. If I don't want to, or if I want to remove this, I can simply right click and delete this current data tip. If I want something on this black signal, okay, maybe somewhere in here, again, I can click on that signal and it'll locate it on the black signal. Then again, I could move it relative to the black signal. Okay, so that gives me a more fidelity relative to my data point. And again, you can always delete that by right-clicking and hit delete. And again, if I want to reset this, I just go back to my zoom and double-click. We can now look at summary plots. You can see that the summary plots are plotted LMA, LF, and WRR based on the settings that we have previously set. Next, from the drop-down, we can select histogram. This brings us back to the summary plots. A set of crosshairs appear. We can select the region of the rope we would like to perform the histogram over. I'm going to pick roughly the beginning of the rope to the end of the rope. A histogram will be performed between the two sections we've selected. Those are identified by these light blue markers at either end of the rope. A pop-up appears asking us if we wish to change our axis settings. For now, I will leave it as is and select OK. And we can accept those settings. A new pop-up appears asking if we wish to set a maximum deterioration zone for the LMA histogram. I will select yes. A set of crosshairs appear. Being that this is a new rope, we would expect the LMA to be very small. I will select a region here just to demonstrate it at roughly just below 0. A pop-up asks if we would like to accept that, or we could redo it. For now, I will accept. The next pop-up asks if we wish to set a maximum deterioration zone for the LF signal. I will say yes for this. Go to the LF signal. So first, I will select a region below 0. For this case, I will redo so I can show an additional feature. Notice the redo clears. I re-get my crosshairs. This time I'll go above the region. And what you'll see here is we select LF to be symmetrical about the 0 point. Previously, I selected a region that was too low, so the top part wasn't highlighted. This looks good, so I will hit accept. Finally, a deterioration zone for WRR. I will say yes and select a region. I will accept this. When this is completed, a message appears in the log space showing that we've performed histogram as well as the regions that we've selected from 16 meters through 3.2 kilometers roughly on the rope. I will now click the image to do a little bit more analysis. The 3 plots you see here are the LMA, LF, and WRR plots that we have seen previously. The new plots appearing on the right are the histogram plots for LMA, LF, and WRR. Note that the x-axis for all is percent. This is a histogram shown as a probability distribution function, so all of this area adds up to 100%. Notice that this is a log scale, so each of these markers is an order of magnitude. Starting from 100%, we can go down to 10%, 1%, 1/10%, 1/100th of a percent, and then here you can see 1/1000th of a percent. Like previous plots, I can do zooming. So for example, maybe I want to see around this 2000 meter mark, so I'll click that tab. And what you'll observe is a correlation. We've chosen the histogram y-axis setting to be the same that we have for the actual signal. So you'll see the LMA goes from +1 to -1, so too does the histogram. So the region that we selected for the deterioration zone, slightly less than 0, you'll see highlighted on the actual rope here. Similarly for LF and also for the WRR. Additional zooming can be had by clicking the zoom icon shown here. I will zoom in this particular region, and notice you can see the red correlating to the histogram. Similarly for the WRR, I will zoom in this region. Notice you can see the tips of the rope highlighted in red that exceeds this value. As a reminder, to reset the zoom, simply double-click. And similarly for the LMA. We can go back to the overview chart, and perhaps there's a region out here that we wish to investigate further as well. So again, looking at this part of the LF and WRR, perhaps we want to zoom in a little bit more here and observe that spacing of the rope from roughly 2820 to 2825 meters in the rope. Perhaps there's something. Again, since this is a new rope, these numbers are very small and are by no means areas of concern for this rope. After the histogram, we can either choose to save figures, or we can go and demonstrate our Vista software. I will now click Vista. Pop-up menu appears. Notice it says just under 36,000 seconds, which is about 10 hours. So in terms of tabs, I'm going to put in 1800 seconds, which is just about 30 minutes per tab that'll show up. Here you'll see the results of the Vista charts where we have our LMA, LF, the first two charts, and then on the bottom chart we have rope payout with the left axis and rope speed on the right axis. The key difference here is the x-axis is now in time, notice seconds here, and so this shows you the actual inspection. A few pieces of note here is when you see the rope speed here go to 0, you'll see it here but more pronounced here, and if we look up at the LMA you'll see that it basically holds the last value, so in this case the inspection was paused for some time. Here again you can see it right here, and the key is looking at when the rope speed is 0, and then you can also see it in the rope payout where you have these flat sections of the rope here during that part of the inspection. So again, during this time the inspector may have paused the operation for some time, maybe to do a visual inspection or a variety of other reasons, and so that's what the Vista actually provides, is a more complete detailed time here. So again, when you look 3.5 times 10 to the 4, that's roughly 36,000 seconds, which when you divide through and get hours, that's about a 10-hour run that you see here. And then the rope, again, looking at the rope payout here, just over 3 kilometers right here, so maybe about 3,300 meters for the full inspection, with a few start-stop cycles in here as well. So that will basically show the benefit of Vista compared to the regular distance charts. And again, even on our Vista plot, we see here specific zooming patterns as well. So again, but notice here we are in seconds, so we might choose somewhere in this time frame here, and that maybe is right before we decided to pause the inspection. Again, you can see the rope speed going down here. We can go back to our overview tab at any time to give us a broader look at the inspection, and again, if we see something of interest, we can always go zoom in that specific area. So maybe right after we paused and came back online, we wanted to inspect something, then pause. Maybe we wanted to we saw something that hit about 0.5% of LMA. Maybe we paused and wanted to look at that a little bit closer, and then again we can proceed with our inspection as appropriate. Epilogue. We consider our Continuous Rope Monitoring System, or CRMS, as a contribution to the digital revolution of the offshore oil and gas industry. To illustrate, please watch this ABS video about smart functionality for marine and offshore assets.
Spurred by increases in connectivity, sensor technology, and data processing, the marine and offshore industries are evolving digitally at a very rapid rate. Smart technologies use advanced analytic techniques to identify data trends and anomalies, providing early indicators to avoid potential failures and downtime. Smart functions support crew and shoreside personnel in proactively managing asset health and performance, improving decision-making. The ABS Smart Guide introduces a unique goal-based approach to help owners and operators qualify and utilize smart functions.
In the development of the Smart Guide, we approached smart functions in the same way that the marine and offshore industries considered their adoption. The goals that the owner or operator intend to achieve are defined first. Then we drill down to the practical steps that are necessary to implement the smart function.
Well, smart technology is all around us. You get in your car every day and your car tells you indicators of health state, things to do from a maintenance perspective. In addition, other industries are already using this technology all over the place. Why not apply this technology to our industry? The assets themselves are already highly digitalized. It only makes sense to put some smart functionality on top of this digitalization and help owners and operators derive the benefits from the application of this technology.
So, how is the industry responding to smart functionality? ABS worked with Keppel Offshore and Marine, applying smart guidance to help meet their goals.
RigCare is Keppel Offshore and Marine's proprietary one-stop solution designed to create a differentiator for our assets through the use of reliable and cutting-edge technology. Our deep technical expertise in marine and offshore design and construction, combined with ABS expertise in qualifying and technical services, enabled us to apply new innovations and digital technologies.
We've been working with Keppel for quite a while now. The idea is to utilize data-centric approaches using analytics and condition monitoring techniques. So Keppel achieves the SMART notation, but ultimately the owners and operators benefit by maximizing the benefits of their solution through helping them with both maintenance planning, dry dock event planning, and also the survey after construction events, ultimately helping them minimize downtime for the rig.